I would like to welcome all of you to AMITA's annual meeting and thank you all for being here. Before we get started with the interesting part, just a little bit of bookkeeping. Um, Following this meeting, so 15 minutes after this meeting ends, we are going to start our business meeting, which is open to all paid members of AMITA. And there will be voting on new bylaws as well as a new slate for the board members for next year. If you're not able to attend the business meeting, there will be information on how you can vote sent to you via email. All voting is currently electronic, so you'll be able to log in and vote. But you have to be a paid member of AMITA to be eligible to participate in any of the voting. And we have a few events coming up this summer. We have the AMITA Connect events being run by Diane Rigos, who is our current membership chair. And they are online and they're just for connecting and chatting. So please join those if you are interested. And they will continue into the academic year with some of them being in person on the MIT campus. Okay, so without any further ado, I am going to introduce our speaker for today, who is the newest Ellen Swallow Richards Professor at MIT, Yael Kalai. She is a cryptographer and a theoretical computer scientist, and she is in MIT's Computer Science and Artificial Intelligence Laboratory, otherwise known as CSAIL. She previously served as a senior principal researcher at Microsoft Research New England. She earned her bachelor's degree in mathematics at the Hebrew University in Jerusalem in 1997, followed by a master's degree in computer science and applied mathematics from the Weizmann Institute in 2001. Her thesis there was recognized with the Outstanding Master's Thesis Prize. She came to MIT and completed her Ph.D. in computer science in 2006, and that thesis was also awarded a prize, the George M. Sprowls Award for Outstanding PhD Thesis in Computer Science. She is the recipient of the 2022 ACM Prize in Computing for breakthroughs in verifiable delegation of computation and fundamental contributions to cryptography. And she became a fellow of the International Association for Cryptological Research in 2022. So without further ado, I give you Yael.
Thank you so much. Thank you, guys. I'm really excited to be here. Nice to see all of you. Actually, feel free to put on your camera. I was told that, this is, and now I see also that my audience is majority of female. I have to say this is very unusual for me. I usually teach to a bunch of guys, and it's really a pleasure and exciting for me to kind of talk in front of a bunch of women. So I'm very grateful. And let me share my screen. Um, oh, sorry. Okay. Can you see my slides? Good, full screen? Okay, great. So I will not be monitoring the chat for questions, but I was told that someone else will monitor. So just let me know if something pops up there. Okay, so yeah, my main area of research is cryptography. And today, with kind of the way the world is changing, my research is focused more on quantum and very recently on AI that I'm not going to talk about here. But what I do want to tell you about is a bit about cryptography and how we at MIT, and actually as a community at large, deal with kind of the threats and benefits of quantum computing. So, okay, so let me first start with kind of a little bit, what is the field of cryptography? So the field of cryptography has been around for thousands of years. Throughout history, it was mainly a form of an art, where, people use cryptography to kind of send messages in some encrypted form to one another. Often these encryption schemes were very much ad hoc, with no kind of scientific reasoning behind them. In the last, I would say, 50 years or so, the field of cryptography has really transitioned from kind of an art to a science. And what I mean by that is I think the way the field of cryptography has been kind of based is it consists kind of three main ingredients. The first is kind of formal definitions. So, what is the definition of, let's say, a secure encryption scheme? So, when I want to send a message in a way that the adversary will not know, or people cannot read what the message is, what is really the definition? What is the power of the adversary? What is the secrecy guarantees that we want? So, kind of actually giving rigorous definitions for our cryptographic primitives. The second ingredient is, of course, constructions. We want to realize these definitions, so we give constructions. And the third and final ingredient is a security proof, where we prove that our construction indeed satisfy the definition. So these are the three ingredients. However, the sad fact about cryptography is that we actually do not know how to give security guarantees. We actually do not know how to prove that a scheme is really secure. Okay? However, what we do know is, or what we do is the following. We say our scheme is secure under assuming some kind of a hardness assumption. So, for example, we can say our scheme is secure, assuming that it is hard, let's say, to factor a large number. That's what's known as the factoring assumption. So, if I give you, let's say, a product of two very large primes, when I mean large prime, think of 500 digits or something like really large prime. If I give you the product, it's easy to compute. When you take two primes, it's easy to compute, but we believe that it's hard to factor. Now, we don't know how to prove that it's hard to factor, but this is kind of an assumption that we work with. So all our schemes are proven secure under some mathematical hardness assumption. Now, this is what we call the win-win paradigm. It has been actually a really successful way of getting around this impossibility result of, or the fact that we cannot actually prove information theoretic kind of security guarantees. And the reason why this has been a good way of giving security guarantees is because it gives us, like I said, this win-win paradigm. Namely, either our scheme is secure, or if there exists an adversary that manages to break the scheme, then we can use this adversary to kind of get a breakthrough in algorithms or in mathematics. Okay, so for example, it's widely believed that factoring is hard. And if there exists an attacker that breaks our scheme, we can use this attacker to actually find an algorithm that factors large numbers. And that can be a huge breakthrough. So we have this win-win paradigm that we like. Okay, so that's kind of the high level kind of structure of our field. Now, what happens when quantum computers come into play? Okay, and when we talk about quantum computers, usually we think about kind of three phases of quantum cryptography. The first phase, which is the phase that I argue we live in right now, it's not a futuristic phase, it's a current phase. And that's what we call post-quant. In this phase, it's a phase where the world is classical. So our devices are classical devices, but we need security against quantum adversaries. So the security guarantees needs to be, even if the adversary, the person attacking the scheme, has quantum power or has access to a quantum computer. And the reason I say this is the world we live in right now is because, today we're encrypting messages to one another. But we want to make sure that these messages are not are still hidden even 10 years from now. Now, an attacker, even though today maybe they don't have quantum power, they can store these messages, these encrypted messages. And 10 years from now, when they will have probably quantum power, they will decrypt it. So because we feel like quantum is, or at least that's what we're told by, the enterprise, by Google, Microsoft, IBM, and so on, that they believe they would be able to factor our current factoring-based schemes in their, they gave us like a 10-year, in the next 10 years. 10 years is not that far from now. So we want to make sure that when we send messages today, we want to make sure they won't be able to be decoded or decrypted 10 years from now by a quantum adversary. And that's why already today we need to upgrade our crypto to be what we call post-quantum secure, or secure even if the adversary has quantum power. So this is the phase one of quantum cryptography. The next phase of quantum cryptography is what we call mini-quant. So here, think of the following. Still, most of us are going to just have access to classical devices, but there may be a few quantum computers out there that we can use as a service. So this is kind of a phase where quantum computers are very expensive. We're not going to each have a quantum computer, quantum laptop, but we may be able to access these kind of large, expensive quantum computers if we wish to. And here in this phase, we need to think of how do we ensure that if we talk to a, let's say, kind of a cloud, quantum cloud or a quantum service, that it gives us kind of the correct output, that they don't learn our private information, and so on and so forth. So that's phase two. Phase three of quantum cryptography is what we call quantumania. This is kind of a futuristic phase where we all have quantum computers, all our devices are quantum, maybe our watches are quantum, the communication is quantum, and wow, a lot of amazing things can happen in this world. So these are the three phases. I'm mainly going to talk about phase one, though I am going to mention a little bit about phase two and phase three, but very, very briefly. So before I go into these phases, let me start by saying so when we go to post-quantum cryptography, let's see what happens to our kind of three ingredients, which is definition, construction, and security proofs. And again, here I'm thinking of the case where the adversary is quantum, but we're all classical. So the constructions are classical, meaning the users using our schemes are classical, but we want security against a quantum adversary. So what happens here? What happens to our schemes? And for a while, we thought that the only problem is that our assumption may be broken using quantum computers. For example, so we need an assumption that is what we call post-quantum secure, okay, or an assumption that we believe is hard even given a quantum computer. And for example, factoring, we know due to Shor's algorithm, professor at MIT in the math department, he showed that actually it's easy to factor if you had a quantum computer. So all our schemes that are based on factoring, if the adversary has a quantum computer, the schemes are broken. So that's a problem. But it's not a huge problem because we have a lot of schemes, especially in the last kind of 10 years, but even before 20 years, that are based on other assumptions that we do not know how to break using a quantum computer. An example is what's called learning with error. So I don't want to go into what exactly it is. Basically, it says that it's hard to solve noisy linear equations that have some error in it. But the details don't matter at all. The point is, we do have assumptions, such as the learning with error, also what's known as LWE for short, that we believe cannot be broken with a quantum computer. For a while, we thought, good, so all we need, or I think still people that are not kind of in this space still believe that once you have a scheme that's based on an assumption that cannot be broken using a quantum computer, then it's post-quantum secure. Namely, we're okay if the adversary is quantum. However, when we kind of dived into, kind of thought about it in a little more depth, we noticed that this is far from true. What we noticed is that actually, even if the scheme is based on a hardness assumption that cannot be broken using, or we believe cannot be broken using a quantum computer, still, we need the security proofs to be post-quantum. Namely, the security proof needs to take into account that the adversary may be quantum. So we need to upgrade the proof, we need to upgrade the constructions, and even we need to upgrade the definitions. Some of the definitions actually are not meaningful if the adversary is quantum. So on a kind of deeper inspection, we noticed that actually we have a big problem here. And the problem is, like, what do we do? Do we need to kind of redo all cryptography from scratch? Like 50 years of rigorous definitions, constructions, and proofs? Do we need to just scratch it and do everything from scratch? And part of what my group at MIT does in this regime is we try to develop, sorry, there's a missing E, new techniques that will allow us to kind of just lift classical cryptography to the post-quantum setting. And I want to tell you a little bit about how this is done and what the issues that come up. But before I do so, let me just give you like a really very, very brief point about what quantum is, what is quantum computation, and what makes it problematic, like, or different than the traditional, what we call classic computation. So quantum computation, you know what, as opposed to classical computation, which kind of the building blocks are bits, it's 0, 1, and we manipulate bits, basically. A classical computer, the storage has bits, like just 0, 1, 0, and 0, 1, and they're manipulated in some way. Like there's and of the 0, 1, or not. These are kind of the basic computation in a classical computer. What happens in a quantum computer? In a quantum computer, we have bits. This is kind of ket notations that are used in quantum mechanics. But in a quantum computer, the basic building block is not a bit, but rather what's called a qubit. A qubit is basically a superposition of 2 bits. So as opposed to just being 0 or 1, it's some combination of 0 and 1. We call it a superposition of 0 and 1, where the coefficients are complex numbers that the sum of squares is 1. Okay? More generally, a quantum state, so classically, if you look at an n-bit state, it's just a element in 0, 1 to the n. So just n bits, n kind of 0, 1, 0, and 0, 1. In a quantum state, again, you have a superposition over all possible n-bit strings with some coefficients. And these coefficients are complex numbers, as here, that where you sum the squares, you get 1. Okay, again, the details are not important here. There's 2 things that are important. The first thing is that when you look at a quantum state, the state changes. This is bizarre. Okay, this is something that we're really not used to thinking about in the classical setting. Here, when you look at a quantum state, it changes. It, what we call, collapses. So if you have a qubit and you look at it, then what you observe either a 0 or a 1. You observe a 0 with probability alpha square, so the coefficient square. You observe a 1 with probability beta square. So and indeed, the sum is 1. So you observe 0 with alpha squared and 1 with 1 minus alpha squared. And the important thing is, when you observe a 0, the state collapses to 0. So before the state went in superposition, after you looked at the state, it changed. Now it's a 0. And if you observe a 1, the state collapses to 1. So this is very, very different from, I would like, this is a fact of quantum mechanics that is very different from classical mechanics. So that's one big difference. The other one, which is a very kind of surprising or something counterintuitive, is what's called the no cloning principle, which says that quantum states in general cannot be cloned. So in classical setting, if you have a bunch of bits, 0, 1, 0, 1, 0, and 0, 1, you can always copy it. You can take a string and copy it. Quantum, you can't do that. You can't take a quantum state and generate another quantum state that's identical to it. This fact that you cannot clone states and that when you look at a state, it collapses, that's what makes kind of our security proofs in cryptography break down. So now let me go to cryptography and tell you why, kind of what the issues that come up when the adversary is quantum. So before, let me first say what security proofs look like in cryptography. So let's say we have some cryptographic primitive, let's say an encryption scheme. And now I want to argue that it's secure. How do I argue under the definition, which I didn't even define, but it doesn't matter. There's some definition, and I want to argue, here's a construction, some primitive, I constructed it, and I want to argue that this construction is secure. How do I argue it? I say, suppose there exists an adversary that breaks this primitive, then I'm going to argue that I can actually use this adversary to break the assumption, to break the hardness assumption that I'm assuming it's hard. That's kind of how it works. So again, we say, suppose there exists an adversary that breaks the primitive, we're going to use this adversary to break the assumption. And therefore, we say either the scheme is secure, or if we have an adversary, we can break the assumption. So we have the win-win that I mentioned. How do we break this assumption? So in other words, well, for example, suppose that we have a theorem that says that this cryptographic scheme, this encryption scheme, is secure if factoring is hard. Then what we prove is that we can use this adversary to break factoring. So given product of 2 prime, this what we call reduction, that's why we use the letter R, we have a reduction that uses this adversary to find the factorization. And therefore we have this win-win. If there exists an adversary, we can factor numbers. That's how our proofs work. Now, of course, factoring is no good. I said factoring can be broken with quantum computers. Fine, there's other assumption, like the learning with error assumption, where here the reduction gets noisy linear equations. Again, the detail is not important, but basically the reduction will solve the linear system, okay? But you can ignore the math. Okay. What happened? So now we have a post-quantum assumption. It seems like things should work even in the quantum setting. Why? Because this reduction that breaks this assumption, it basically uses the adversary as a black box. It doesn't care how the adversary is implemented. It just kind of gives the adversary questions and looks at the answers. So in some sense, why should this reduction care if this adversary is classical, quantum, uses another method? I don't know, maybe there's a quantum plus out there, whatever. It seems like, what does it matter? He just sends questions, gets answers, and uses these answers, he's able to break the assumption. And so the proof should just go, so the proof goes through even if the adversary is quantum. And this intuition is really why the community indeed thought that, if you have schemes that are secure under a post-quantum assumption, it's post-quantum secure, period. So why is it not the case? I just kind of argued that because the reduction uses the adversary In a black box, doesn't matter if the adversary is implemented using quantum or classical or whatever. So why? What goes wrong with the argument? And the issue is the following. So the answer is no. The fact that it's black box does not mean it extends to the post-quantum setting. And the reason is that the reduction, it runs the adversary many times. So it gives the adversary one question, gets an answer, then it gives him another question, then gets an answer. Or you can think of it, it gives him some ciphertext, sees if he decrypts it, then gives him another ciphertext, if in the case that the construction is an encryption scheme, and sees if he decrypts it, and so on and so forth. The problem is that when the reduction runs the adversary has some quantum state. We denote it by psi, but it has some quantum state. When the adversary gives him an answer, the quantum state changes. And now, to run him again, we need to get back this quantum state. But we don't know how to get back the quantum state. And the reason why is because there's this no cloning principle. We can't, if we could start with this quantum state, multiply it kind of many, many times, like copy it many, many, many times, then yes, it will work. Like the proofs will extend. But we can't copy the state many times because of the no cloning principle. So we run A once, we get an answer, the quantum state is gone, and now we can't run A again. So, but in order to break the assumption here, we need to run A many times. So that's why our proofs break. So now what do we do? That's a big problem. So what do we do? And what I want to say, this is not just a technical issue of the proof. Actually, we have examples of constructions that are proved secure under a post-quantum assumption, but we know it's not post-quantum secure. We actually can break it using a quantum computer. So it's not just a matter of like the proof breaks down, it's the construction can break down. Like the construction can actually be insecure, even though the assumption is post-quantum secure. And I just want to mention that this fact has been used actually to get what's called a proof of quantumness. So let's say I want to prove to you that I have a quantum computer. I want to tell you I have a quantum computer. And you're like, I don't trust that you have a quantum computer. I say, yeah, I have it. You're like, prove it to me. So I'm going to show you, I'm going to break this primitive. And classically, we don't know how to break this primitive. I broke it. So now you know I have a quantum computer. So the fact that we have primitives of this that are secure classically but not secure quantumly is a big problem, but it was also used as kind of as a feature to get kind of to prove quantum, what's called quantum supremacy, or that I own a quantum computer. Okay. So now going back to what, our goal, which is we need to upgrade security to the post-quantum setting. And ideally, I want to do it without redoing all of cryptography from scratch. So how do we do it? So the first idea was that it's true that we cannot clone a state, a quantum state. As I said, quantum states cannot be cloned. However, what we can do is repair the state. And what I mean by repair, I had the state psi, I ruined it. I can't go back to psi, but I can go back to state that's some psi prime, a different state, that the adversary can still succeed with this state. So a state that you can give the adversary and he will still be able to break the scheme. It's just not the original state. So this seems like, okay, great. I can still recover the proof. Why? So now my adversary has some quantum state. The reduction will use this adversary to break the assumption. He will feed it some question, some query, maybe a ciphertext, and try to get an answer, maybe the message, the decryption, or whatever it is. When A gives an answer, its state changes. This is not a good state anymore. This state is a collapsed state. A doesn't work well with this state. However, now I'm going to repair the state. And once I repair the state, I can run A again. So that's great. Let me first just mention, I can't, the repairing the state takes exponential time in the length of the answer, so it doesn't always work. It works for some situations, but it's pretty general. It works in many cases, so I'm happy. And now in the repaired state, I can run A again. That's kind of the idea. Still, there's a problem. Still, I cannot use my proof as before. And the reason is that this repaired state is a state that the adversary with this repaired state, it's good on average. It works on average. However, it may not work well on specific queries that are similar to Q, that are somehow related to Q. So this state may remember this query that was given to A and may not work well on queries that are quote unquote similar to this query. Now, in our reduction, we usually send the adversaries questions that are very related. And it may be that on these related queries, this repaired state will not work. So in other words, the problem is our proofs assume that when you run the adversary again, you run it on exactly the same state as it had. Namely, on the queries that the original A succeeded in, when you run him again, he succeeds in the same set of queries. Now, you change, in some sense, you change the adversary because you change its state. And this morphed state is different. It succeeds on different queries. And now our proofs again can break down. So that's a problem. However, what we were able to do then is to give a better repair. And what we call it is like a memoryless repair. So we can repair this state to a state that actually forgets information about psi. About Q. So what we can do, we can take a state, we run the adversary, the state collapsed to a bad state. But then we can repair it to a new state, psi double prime. This psi double prime is not the same as psi, but it's not related to Q at least. It doesn't have a memory about Q. So the set on which the set of queries on which this psi double prime is good for has no dependence on this query Q. And this allows us to kind of use the old security, the old proofs. So by saying, look, I can take the old security proof. All I need to do is to repair the state in a memoryless way, and then I can kind of regain my old security proof. So in this sense, we kind of were able to lift a big chunk of cryptography to the post-quantum setting. And again, it's not all cryptography. There's still this kind of 2 to the A business. So it's only for primitives where the answer is short. So we still have a lot of work to do, but at least we're at it, and we have some techniques that are useful for us. So let me end by just saying a few words on phase 2 and phase 3, on mini-quant and quantumania. Okay, so for mini-quant, here, as I said, now suppose there are a few quantum computers out there. So here's like a quantum cloud. I'm a user, and I want to use this cloud. So I want to tell him, here's my input, here's some quantum circuit, and can you do this quantum computation for me? And he gives me the answer, so I'm happy. And I maybe pay them to do for their service. What are the issues? First of all, I may want confidentiality. I may not want the server to know my input, to know the circuit I want to compute. So there's a problem of confidentiality that I want to maintain. And we have developed actually a really nice tool that is called quantum fully homomorphic encryption, where actually we can have the cloud do this computation without learning anything. So he's completely blind. He's able to do this quantum computation blindly, without knowing my input, without knowing the circuit. This is really counterintuitive. It's kind of surprising that it's even possible, but turns out it's possible. This is part of kind of the magic of cryptography. So that's one thing we can do. The other issue is integrity. So how do I know that he's giving me the correct answer? And note that actually the server has the incentive not to run this quantum computation because quantum computations are expensive. So maybe the server has the incentive. I give him a circuit and an X, maybe hidden, and he tells me, yeah, the output is 1 without doing any computation. How do I make sure that he actually does the computation? So even here we have what we call classical proof of correctness of quantum computation, and we have built techniques that show how the server can actually prove to me that this is the correct answer, even though I'm classical and he's quantum. So we can prove to a classical user using a classical proof that this is indeed the outcome of a quantum computation. So these are kind of two magic ingredients that we were able to come up with in the last, I don't know, 8 years of 7 years or so. And there's a lot of work on improving them and so on. Okay, and then the last minute, let me just end with kind of the real big magic that can be done in the world of quantumania, where everyone has quantum computers and the communication is quantum. One thing that can be done is we can have quantum money. So what do I mean by quantum money? So currently the money we have is this funny, paper that we give one another. We want to go to a digital world where we just give digital money. Bits 01000 is worth $100. Now, of course, you can't do that because anybody can copy, bits. So that doesn't work. In quantum, there's no cloning principle. So it turns out that you can use quantum to get what's called quantum money. So you can just send qubits, and that will be like you can use qubits as a form to get quantum money. So that's kind of inspiring or interesting. Two other examples I want to give is one is we can do what's called certified randomness. This is really counterintuitive and bizarre. So let's say I generated randomness and I tell you, oh, I generated randomness. The output was 0011100101. You're like, how do I know that you generated randomly? I told you, yeah, I flipped coins. Like, how do I know? Not to mention that flipping coins is not really random, just we don't understand enough about the laws of, Newton and we can't compute. But, if you were an amazing physicist, you can compute everything and know that it's actually deterministic. But let's say I told you, no, I generate randomness, this is the outcome. How do you know that it was random? Maybe it's not random. Using quantum, I can give you the sequence of bits, 00110001, with a proof that they were indeed generated randomly. This is really, I don't know, amazing. I remember when, this is a paper of one of my students, and I remember when I looked at it, I was just blown away. I could not fall asleep that night out of like, wow. Another thing we can do using quantum cryptography is what's called certified deletions. That's also something that's really interesting. So today, for example, when you give your data to Google, now to all these LLMs, OpenAI, whatever, they can store your data. They can then sell your data. They can do a lot of things with your data. This is a big concern today. Using quantum, so they can tell you, oh, don't worry, I deleted your data. How do I know that? How do I know that? Data is worth a lot of money today. How do I know that they really deleted my data and it's not stored somewhere? Using quantum, we can prove that the data was deleted. Again, that's super counterintuitive. Like, how do you do that? but we can do that using quantum. So this is just to end kind of the talk on a positive note about the magic that can come with quantum as opposed to just the problems that it gives us cryptographers. So this is a world where there's a lot of kind of interesting new things coming up, a lot of really cool ideas, uh, primitives, new, really nice mathematics that comes out of it. And we're really, I don't know, me, my students, and our community are really having fun working on this. So I'll end with that. Thank you so much. And maybe I'll stop sharing the screen, maybe. So,
Yeah, thank you very much. So we have a lot of really great questions. And if you have questions, you can continue to type them. We have a good amount of time for Q&A. All right, so the first question is from Divya Sinha, who asks, how does the qubit format how does the qubit format improve computation speed and or power compared to the 0, 1 classical format?
good, good, good. Great question. So what really gives so I didn't say it all, I didn't talk about it, but I didn't say how these quantum states are manipulated. So I said classical states are manipulated. You can do an or, not. That's how we manipulate classical bits. Quantum bits are manipulated using what's called unitary matrices. But forget about the math. What happens when you apply a a quantum operation to a quantum state is basically because the qubits are entangled, is what I say, that entangled. You're basically applying a computation on all of them in some sense at once. So let me maybe explain this a little more rigorously without going into the math. Here's when you have n bits, you have n kind of n bits of information, if you will. When you have n qubits, in some sense, you have 2 to the n information because you have 2 to the n coefficients. An n qubit state is like a superposition over all n qubits. So the number of coefficients is like 2 to the n. Now, when you manipulate n bits, in some sense, you manipulate 2 to the n bits of it, 2 to the n kind of information together. And this is what sometimes allows you to get this exponential speed up. That's kind of the basic idea, but to explain in more depth, I need to, it requires some time and, it's technical.
And
So, but that's a great, great question.
And a chalkboard and
Yeah, I have one right now.
hour. Yeah. Okay. We have a whiteboard behind you. Okay, the next question is from Sarah Simon. It says, congratulations on being appointed to the ESR chair and your many other awards. Where did you work outside of academia, if anywhere? How was the atmosphere for women there as compared with MIT and other university experiences?
Great. So okay. First of all, I feel like my entire life I was an academic, even though for 15 years I was in Microsoft Research, but that environment is very much academic. So people ask me, did your work change a lot from going to Microsoft MIT? And the answer is almost none, really. I had students working in Microsoft, and I did research, and I was a member of the academic community, and that part I don't feel like was very different. So I feel like I have been really an academic throughout my career. In terms of being a woman in science, that's a big one. I have to say, I was lucky, even though I take credit for it. It's not just luck. I ended up in places that were very, very supportive towards women. MIT, I think, is a heaven for women. For example, I mean, I feel super supported at MIT. I felt that way as a student at MIT. My advisor was female too. Shafi Goldwasser was my advisor. And I always felt like they're very strong women around me. Uh, and it felt, I never even noticed actually that there was that it's an issue that I didn't notice that I was in such a minority just because the women were so strong and fantastic that and the and it sets a tone. The guys were great, like people were very supportive. There was no issue, you know. Um, in Microsoft Research, similarly, the head of my lab was Jennifer Chase. She's also a woman, a fantastic one, and led the lab in a very, very kind of supportive way for women and other minorities. So I was very lucky. That wasn't the case always. So I have a question. Is this recorded and going to be public, or is just us
It's being recorded.
in public?
It will be posted. Yeah.
Yeah. So I should be careful about saying, but let me just say, it was not, I did not always feel that way in every, you know, but what I learned is to leave very fast a situation that I felt was not, you know, not supportive for women or for me. So I always tell when I give talks to female students usually, which is it's one of my favorite things to do, or when I'm in a panel in front of female students, or actually it's not even, it can be for anyone. It's not just female. Just female tend to get more, it's issues come up more often, but it can come up for other minorities or not minorities, just for people. When you're in a situation where you don't feel like you're valued or that's not working well for you, move. Don't stay because it's you can never, like, for me, I felt like to do good work, I need the support of people around me. Like I want to feel good in the place I am. When you're in a family that's not supportive of you, you sink, and you need to be in a family that lifts you. And so I kind of moved to a place where, you know, eh, that was my family. So I always surrounded myself in such families. And by the way, today I have to say our crypto group at MIT has a majority of female students,
Hmm.
which is like super fun, super fun. And not like and amazing students, not just, like super strong, uh, like inspiring, fantastic female students. So
Yeah, that's great advice. If you're not being supported, go to somewhere where you are. That's really, really important for all of us.
yeah.
All right, so there's a whole bunch more questions. I don't know if we're going to have time to get through all of them, but I'm going to try. All right, so Divya Sinha has another question. Okay, this one's technical. So it says Cx here is analogous to C being a function of variable x, right? So
Yeah.
if so, it can't wrap up how it can compute the answer without even knowing C, even if the output can be made in terms of the variable x, it needs to know the function C, right?
Yeah. Okay. No, it doesn't need to. So you're talking about the second part, like the mini quant, where I said the quantum cloud, can compute C of x without knowing C, without knowing x. And the way it does it, it doesn't even know the output C of x. What it does basically, like the idea is, the client, will give him an encryption of x and an encryption of C. Now he computes kind of his quantum thing, he manipulates things under the encryption, and he gives me back an encryption of C of x. So he's actually blind the entire time. He doesn't see a thing. But there's a way to do these quantum manipulations under the encryption, and at the end get the output under the encryption. So I hope this
Yes, thank
answers
you.
your question. Yeah, you have great questions, so thank you.
Okay, Divya, did you need to follow up, or is that good?
Oh no, that's great. Thank you. Now I understand the encryption part. I was just thinking very classically. Thanks.
Yeah, no, great, thank you.
Okay, here's another really good
Wait,
question.
may I quickly ask a follow-up?
Yeah.
Is that similar to what we have in TPM these days, trusted processing modules, where computation are done in a secure enclave?
Good. It's not the same.
Okay.
There, what happens is they assume that there's uh, hardware
Mm-hmm.
that you put things into the hardware. So you have the encryption, you put the encryption into the hardware. The hardware has a secret key. It decrypts. He does all the computations in the clear. It just nobody can look into, nobody can,
Yep, yep,
and then he outputs things encrypted. So
yes.
here, there is no secure enclave. There's no hardware that does things securely. So,
Okay.
but it is very related. It's the relationship is indeed that, like you got it. So
My mind is blown. Thank you.
Well, the next question is from you, Antu Vo. So how does quantum money break or not break cryptocurrency as we know it today?
good, good, good. So okay. So cryptocurrency, as I mentioned about quantum money, I thought maybe I should say something about cryptocurrency, but I didn't. I didn't want to take more time, so I didn't. But cryptocurrency is, first of all, today the cryptocurrencies they do rely on assumptions, and the assumptions are post-quantum broken, by the way. So if you
Yep.
do Bitcoin or if you go to Ethereum, there's a lot of companies out there, so I can't speak on all of them.
Yeah.
But the two big ones, Ethereum and Bitcoin, which are the biggest ones today, they use cryptography that's not post-quantum secure. So they will need to upgrade their schemes,
Hmm.
which, as far as I know, they didn't do that yet. But they probably will at some point. Um, but I did say that quantum, like classically, you cannot, that you can have quantum money, digital quantum money classically. But actually, there's Bitcoin out there that does do, in some sense, you can think of it as digital money. So, it seems like what I said is wrong. However, the reason Bitcoin or Ethereum or these quantum currencies, the reason they work is they assume this kind of infrastructure, which is we all agree on what the transactions were. So it's like it's written somewhere in the sky what all the transactions were. And without that, you can't have, this digital money. It's only assuming there's like this public ledger that has all the kind of the transactions that ever happened in the universe. And that's what kind of enables the classical, because now the a money is not just a bunch of bits. It's like it contains like a signature that tells me I can give you the money is like me signing that I took a transaction that I got from someone else on the blockchain on the ledger, and I'm transferring it. So basically, all the money is like saying, oh, take this, transfer, like take this part of the ledger, this money on the ledger, transfer it to this wallet, and take this and transfer it to this wallet. So it's just a bunch of like transfers from wallet to wallet. That's kind of what the chain consists of. Just kind of move money from here to here, from here to here. A, but without this public ledger, you won't be able to do it. So with quantum, you can just, give a quantum state. That's money. It's not, you don't need, it's not, you don't need like a, agreement on a
You
huge
don't need that
public.
layer. Yeah. Thank you.
All right, so we're at 12:58. We have time for one more question, even though there are a few more in the chat, but we're just going to do the next one, which is Sarah Simon. Does this line of work relate to machine learning or generative AI?
Does what's again? What's the beginning?
Does this line of work,
Yeah. Okay, yes. So I mentioned at the beginning that now we're starting to think about AI because we have to. And one thing, it is very much related to AI. And I'll tell you. So cryptography. My husband, by the way, works in OpenAI, and he's like, you have to start. You cryptographers have to start thinking about the problems that the world is throwing at you because you guys have the expertise. And what do I mean by the expertise? We think adversarially. In cryptography, there's always an adversary, and we're very used to thinking, what do we do in the case where there is adversary? And what we offer is robustness, namely security, even if in the existence of adversarial parties. Now, with the AI today, this is a big, big concern. Okay. It's a big concern that, for example, even today, when we use these language models. We get answers. How do we know that they're correct? This is a big problem. You know, people ask these AIs, what dose should I take? They use it as medical consultant, as a consulting in many, many ways, and they just give wrong answers. And how do you know? They don't even tell you, I don't know, or very small probability, but if I had to guess, they just very strongly say, I'm sure, I'm confident this is the answer, and it's wrong. So how do you do verification or robustness in this setting, or even confidentiality in this setting? You know, so definitely we cryptographers are now very much kind of that's kind of our new obsession, is making these AI models what we call robust.
Okay, thank you. We have more questions, but it's 1:00 now. So we're gonna have to stop there. I apologize to those questions that didn't get answered. Thank you so much, Yael, for sharing your work and your personal observations. And Kim just put that in the chat too. For those of you who will be attending the business meeting, we're going to take a little break just to give everybody a chance to stand up, walk around, do what you need to do. So we will, if you're attending the business meeting, it's a different Zoom link and it starts at 1:15 p.m. And I thank everybody for coming. And thank you so much, Yael. This was
Yeah, thank you so much. I really enjoyed talking to you. Thank you.
Thank you so much. We hope you'll come back again.
I would love to. Thank you.
Perfect.
Bye.